Okay, so this is a joint work with Neer Alon, Amit Kumar, and my student Anup Bhattacharya was soon going to graduate. Well, this talk was supposed to be given by him, but unfortunately there were some visa issues and he was not able to make it. Okay, so let's straight away go into the problem. So the k-means clustering problem is actually very easy to understand and visualize. So the problem is the following, right? So you're given n points in R to the d, and you're given an integer k. You're supposed to find k points. These are called centers, such that the sum of squared Euclidean distance of each point to the closest center is minimized. That means this kind of objective function gets minimized. So for example, consider this simple 2D example where you have k is equal to 4 and d is equal to 2. So if you're given these black points, then you're supposed to output these red triangles such that the sum of square of distances of these black points to the closest red triangle gets minimized, right? And this also, it's very easy to see that this kind of, this is also going to give you a clustering of the given points, right? So because you can just do a Voronoi partitioning and that gives you a clustering of the given points. Okay, so now this is one of the most widely studied clustering problems, and various kinds of results are known for this. In fact, the complexity situation is pretty well understood. So on the lower bound side, we know that for any interesting values of the parameters, for example, the number of clusters or the number of dimensions, for any interesting values of these, the problem is NP hard. And moreover, it's also known that you cannot approximate it to more than a constant factor, better than a constant factor, right? So this kind of a result is also known, right? So you cannot approximate it better than 1 plus epsilon for a particular constant epsilon. Okay, so on the upper bound side, again, so we have various approximation algorithm that is known for this particular problem. This list is a very highly truncated list. It goes on and on. So it's a huge list. Okay, and various kinds of approximation algorithms are known. So there's polynomial time, order log k approximation, polynomial time, efficient constant factor approximation. And you also have a 1 plus epsilon approximation algorithms, but they have an exponential in one of the, it's exponential in one of the parameters, right? So then what are we going to talk about? Well, so because I guess of the importance of this problem in machine learning and various other fields, various results of beyond worst case flavor have been attempted for the k-means and other clustering problems. For example, clustering mixture of Gaussians. Another line of work is clustering under separation assumption on the data set. What this means is that you try to cluster data sets which have optimal clusters separated in some sense, right? So and the various notions of separation that are defined. And the working philosophy as to why this kind of thing is okay to think about is that the data set, we can argue that the data set is clusterable only when it satisfies some separation. Otherwise, the data set, it doesn't even make sense to cluster data set, right? It only makes sense to cluster data set if it is clusterable. And clusterable means that the clusters are separated in some sense. Now, there are various notions of separation that have been defined in the literature. And people who are aware of the literature know what these separation conditions mean. ORSS, BBG, there are various of the list. This is actually pretty elaborate. Okay, so now the third line of work, which is what we're going to talk about, is clustering in a semi-supervised setting, where the clustering algorithm is allowed to make queries during its execution. Right? This is a sort of a fairly new notion. Okay, so even for this, you have a list of possible candidates. So what we are going to talk about is one model that was defined recently by Ashtiani et al. In a NIPS paper. This is called the semi-supervised active clustering framework, where the clustering algorithm can make same cluster queries. Okay, what this means is that, look at this very simple case, right? So what this means is that the clustering algorithm, during its execution, it can give an oracle 2 points, and the oracle returns whether the 2 points are in the same optimal cluster or in different optimal clusters. Right? It's very simple to imagine this kind of situation. Okay. Okay. So now, so it's not outrageous to imagine situations or contexts where this kind of same cluster queries are possible, right? So people in machine learning are okay with this kind of a model, right? Or if it's too strong, we may think of some weaker version of same cluster queries, right? So to understanding the power and limitations of this idea may open interesting future directions, right? So that's how I'm trying to sell this idea, right? So this is just the starting point, right? So we may think of other results of this particular flavor. Okay. So now, what can we do with same cluster queries? Okay. So well, clearly, if the clustering algorithm is allowed to make order n square queries, quadratic number of queries, you can output the optimal clustering, right? Because you're going to ask for every pair of points whether they belong to the same cluster or not, right? So it's very simple. You give an order n square queries, you can output the optimal clustering. Now the interesting question is whether you can do clustering, whether you can output optimal clustering or something that is close by only making some very few number of these same cluster queries, right? So some basic results are already known, and this was given by Ashtiani et al., who defined this particular framework. And the result goes as follows. So they give a randomized algorithm that runs in this kn log n time and makes these many number of same cluster queries and returns an optimal clustering for a data set that satisfies some separation guarantee, right? So it's an efficient algorithm, and it's not making too many number of queries. It's making small number of queries, and it's going to output an optimal clustering given that the data set satisfies some separation guarantee. Right, and they also show that this separation guarantee is, the problem doesn't become easy if you are given the separation guarantee. The problem remains NP-hard even in this separation guarantee, right? So there is something interesting going on in this particular result. Okay, so a few things to note about the above results are the following. First of all, this is an exact clustering result. So they're going to give exact optimal clustering. Okay, and the result holds given that the input data set satisfies certain separation guarantee. So it's clear from the statement. And finally, another thing to note is that the number of same cluster queries is not independent of the data size n, right? So it's dependent on the data size. Okay, so now since we extend their theory, this framework, to approximate setting, I can just give our contributions by comparing it against theirs. So here's our contributions informally. So first of all, we extend the theory to the approximation setting while removing the separation requirement, right? So our results will not require the separation guarantee, right? Now the second contribution is that we give bounds on the number of same cluster queries, which interestingly is independent of the data size n. Okay, so if you're allowed to output 1 plus epsilon approximation solutions, then you can just make the number of queries that you'll require to make is independent of the data size. Okay, and more interestingly, we extend our results to faulty query setting, where the answers to the same cluster queries may be incorrect. Okay, now this is a more reasonable setting if you want to use this in the machine learning setting, right? Because you can imagine, right? So you can imagine setting up I forgot the name, but you can ask some humans to give 2 points and tell them do they look same or not, right? And if you're making few number of queries, crowdsourcing, right? So, and then you can get these outputs and try to cluster the data nicely, right? And you can imagine a situation where the humans are going to make a mistake with some probability, right? So this is a more interesting setting. Okay. Okay, so let's look at our main results more formally. So we give our main result is the following. So we give a randomized query algorithm that returns a 1 plus epsilon approximate clustering for any given data set. The algorithm is efficient, and it only makes polynomial poly k over epsilon same cluster queries. Right, so it's an efficient algorithm that returns a 1 plus epsilon approximate solution and only makes polynomial k over epsilon query. Okay, now we support it with a lower bound. We show that that any C approximation for a particular constant C, for any C approximation query algorithm that is efficient, needs to make k over polylog k same cluster queries given that ETH holds, right? So we give a conditional lower bounds on the number of queries that any efficient algorithm needs to make to get a approximate solution. Okay, and we also give a faulty results for extend this for the faulty query setting, and the faulty query setting that we are looking at is actually a little bit restrictive, but it's a starting point, right? So the faulty query setting that we are looking at is the following. So our results can be extended to a setting where the response to every same cluster query is incorrect with probability at most q, which is less than half. Yes?
What is ETH?
Exponential time hypothesis. Yeah, so we can talk later what exactly the statement of the ETH is. Yeah. So it's a probabilistic oracle, right? So that means so independently for every same cluster query, it's going to make a mistake with probability. So it's a randomized answer that is returned. Yeah, so it's restrictive. Yeah, so but it's just a starting point. Okay, so now let me spend a few slides in explaining the main idea of the query algorithm. So the query algorithm is basically an algorithm that makes same cluster queries and try to cluster the given data set. Okay, so now one of the main lemmas that we'll use is a lemma by Inaba et al. So the technical lemma is a little bit involved. So let me explain intuitively what this actually means, right? And you can very easily pass for what is going on over here. Okay. Now what this lemma essentially says is that if you're given a bunch of points, right? So given a set of points, okay? Then the center that optimizes the sum of squared distances, okay? That means the one means cost is the centroid or the mean of all the points. It's a very simple result that you can. It's very simple to argue that that's going to be true. Now what this lemma essentially says is that if you have a small uniform sample of the given points, suppose you have poly 1 over epsilon points, okay, from uniformly sampled from the given data points, and you take the mean of that, okay, so that means if you have a sample, if you uniformly sample these green points and take the mean of the green points, then it's a pretty good estimate, right? It's to the cost, right? It's a 1 plus epsilon approximate solution to the one means problem, right? So you can approximate the optimal pretty well just with a small subset of points. Okay, so that's what this lemma essentially says. Okay, so let's try to get a query algorithm just using this lemma. In fact, we can try to do that immediately. So let's look at a simple easy case. Okay, so the easy case is that the optimal clusters have roughly the same size, so they are sort of balanced in some sense. So look at this situation where you have 3 clusters and they are balanced, they are roughly equal number of points. Then can we come up with a query algorithm? Yes, it's very simple, right? So what would you do? Well, we'll just sample poly k over epsilon points uniformly at random from the given data set. Then use same cluster queries to partition them, okay? And then use the Inaba's lemma to get the center, right? And cluster the data point. That's it. We are done. So we sample poly k over epsilon uniformly at random. What that gives us is that since these clusters have roughly the same size, you'll get good representation from each of these clusters. Okay, so you get poly 1 over epsilon representation from each of the clusters, which are uniform representations from each of the clusters, and just use the Inaba's lemma. You can partition them using same cluster queries, and then you will get a 1 plus epsilon approximation, right? And how many same cluster queries you will use? Some poly k over epsilon. That's it, right? Because you just ask same cluster queries over the subset of data points that you have uniformly sampled. Now the general case is what causes the problem. So this idea is going to fail if some clusters are really small compared to the other. Okay, so look at this particular case. Uniform sampling does not work anymore, because if you uniformly sample, well, the big clusters are okay. You'll get good representation, poly 1 over epsilon. But the small clusters, you may not get any point from there, right? So you'll not be able to sample a good center from that particular cluster. So what would you do, right? So what is the natural idea in this particular case, right? And the natural idea is what actually works. Well, so the general case is you have these clusters which may be of very varied sizes. So the natural idea that works in this particular setting is called d squared sampling. Okay, so after finding the first center using uniform sampling, the first center is fine because we have a biggest cluster and we're going to get a good center from there. So after that, there is an issue, right? So after finding the first center using uniform sampling, we'll find subsequent centers is what is known as d squared sampling. And this is the kind of technique I've been interested in over the past few years. And the d squared, it's a very neat, intuitive idea, a very simple idea. So what you do is you just do a bias sampling that gives preference to points that are far away from the already chosen centers. Very fairly natural, right? So that's what you would do. So you already have found a good center. Now you would try to sample not uniformly, but using a bias distribution, favoring or giving preference to the points that are further away. If you do that, then even if there is a very small cluster that's far there, okay, so the probability of sampling from that cluster gets boosted. And there's a good chance that you're going to sample from that cluster, and then you apply the same kind of ideas. Okay. Now, there are various technical issues that you get into because of this. Now, your sample is no more uniform. It's a non-uniform sample. So, because this point is more likely to be sampled than this point, which is closer to the center and so on and so forth. So, the remaining part of the paper is basically dealing with that technicality, right? So, we have been we have been designing various tools and techniques to be able to deal with this kind of technicality. Right, so that's the whole idea of the query algorithm. Right? Okay, so now, let's talk about some other results that we have in the paper. So we have query lower bounds. Now our query lower bound is obtained by showing that any approximation algorithm whose running time has polynomial dependence on n and d, the number of points in the dimension, will have exponential dependence on k. Right, and so how does that give you a lower bound on the number of same cluster queries? Well, you can try out all possibilities for the same cluster queries. That's how you get it, right? And this is done via a sequence of reductions, ETH, PCP. We see vertex covering triangle-free graphs, and this is a result by Avasthi et al., which is a sort of a crucial in this whole chain of reductions to k-means, right? So it's something standard. There's no complication going on as far as these reductions are concerned. Okay, as far as faulty queries setting is concerned, we crucially use results about recovering clusters in the stochastic block model. What that basically means that our kind of techniques gels well with the techniques of recovering clusters in the stochastic block model, SBM, right? And we also get a variant of a popular algorithm called k-means plus plus. Okay, our ideas give a very simple constant factor approximation algorithm in this framework, SSAC framework, using the well-known k-means plus plus algorithm. We know that k-means plus plus cannot give you better than log k approximation, but if you make this tiny same change involve this same cluster queries, then you can turn it into a constant factor approximation algorithm. Alright, future directions. Note that there is a gap between the upper and the lower bound, and our lower bound is conditional. And we don't know whether we can make it unconditional lower bound, okay, and whether we can close the gap between upper and lower bounds. And more interesting thing would be to explore faulty query settings. So our current model is a little bit restrictive, okay, but that's only the starting point. So more interesting results will be whether you can talk about similar kind of thing in more interesting faulty query settings. Okay, that's it. Yeah, so you'll get the same answer. Yeah, that much is. Otherwise, it becomes easier, right?
So the faulty query model is somebody will query processor calling behind your back to say for this particular query is it going to be right or wrong.
Exactly.
After that, they stick to that.
Yeah, they stick to that. That's a model.
What's a good model?
Yeah, so that's also an interesting. So I would consider maybe adversarial, right? So certain Q fraction of the queries can be wrong, right? And they can be chosen adversarially. Maybe it's too strong. I don't know. So, but that's the right model has to be somewhere in between.
So what about model which depends on the distance between the points?
That would be interesting. Yeah. So we haven't thought about that.